Welcome to the Deep Dive. We sift through complex topics to give you the core insights you need.
And today we're tackling chemistry, specifically how chemists, well, talk about reactions, predict them, and even make them more efficient.
Yeah, and to start, think about something really specific and kind of dangerous. The fugu fish.
Ah, the puffer fish.
Right.
Right, a delicacy in Japan, but parts of it, the liver, the ovaries mainly, have this potent neurotoxin, tetrodotoxin. Deadly stuff.
And what's wild is chemists have actually made this stuff in a lab, synthesized it.
It's incredibly complex, though.
That's the thing. One way takes like 32 steps. And the overall yield, it's tiny, 0.52%.
Wow.
Another route, 67 steps, and it's only slightly better, 1.22% yield.
Barely anything.
So it makes you wonder, right, how on earth do they even measure that? Or predict what they should be getting from something so intricate?
That's exactly the right question, and it leads us right into our goal for this deep dive, to give you a clear path to understanding those core chemistry concepts, the ones that let us interpret, analyze, and predict chemical changes.
We're digging into the fundamentals from general chemistry. Things like chemical equations, figuring out reactions, calculating amounts. The basics, but the really important basics.
Right. The mission here is to provide you with some, let's say, shortcuts to really getting how chemical reactions work from the ground up.
Okay, so our sources are rooted in general chemistry, specifically chemistry, atoms first. We're looking at chemical equations, analyzing reactions, calculating products.
The language of chemistry, essentially.
Let's start there then. What exactly is a chemical equation? What makes it useful?
Think of it like a chemical sentence. Seriously. It uses symbols, abbreviations, to describe precisely what's going on in a reaction.
So you've got your starting materials.
The reactants, yeah, they're on the left side of the arrow. And then the arrow points to what gets formed the products.
Like NH3 plus HCl, NH4Cl.
Perfect example. Ammonia plus hydrogen chloride yields ammonium chloride. Simple, clear.
And those little letters in parentheses, G.
Physical states. Super important. G for gas, L, liquid, S, solid, and AQ for aqueous, meaning dissolved in water.
So NH3G plus HClG, NH4Cls tells you even more. Two gases react to make a solid.
Exactly. Maximum information, concisely. You might even see symbols over the arrow, like a triangle, delta, big, meaning you need to add heat.
Okay, so it's a compact way to describe the what and how. But you mentioned a core rule, something fundamental.
The absolute bedrock, balancing. Chemical equations have to be balanced.
Why, though? Just to look neat?
No, not at all. It's the law of conservation of mass. You can't create or destroy atoms in a normal chemical reaction.
Dalton's idea, right. Atoms just rearrange.
Precisely. So if you start with, say, 3 carbon atoms in your reactants, you absolutely must end up with 3 carbon atoms in your products. No exceptions.
And we make that happen using coefficients.
The stoichiometric coefficients.
Yeah.
Those numbers you write in front of the chemical formulas, they tell you the ratio, how many molecules of each thing you need.
It's like adjusting the recipe amounts.
Exactly. And the crucial point, the thing students sometimes get wrong, is you only change the coefficients. Never, ever touch the small subscript numbers within a formula.
Right, because changing H2O to H2O2 isn't balancing water.
No. You've made hydrogen peroxide, totally different chemical.
Okay. So balance by changing coefficients. Any tips for doing it?
Usually best to start with the most complex-looking molecules first, then balance elements that appear in only one place on each side, save elements that appear by themselves, like O2, for last.
Makes sense. Like with burning propane, C3H8 plus O2 ACO2 plus H2O, you'd tackle the C and H first.
Right. You see 3 carbons on the left, so you need 3 CO2s, 8 hydrogens on the left, so you need 4 H2Os. Then you count the oxygens on the right. 3 times 2 is 6, plus 4 times 1 is 4, so 10 total. That means you need 5 O2s on the left.
Giving you C3H8 plus 5O2G plus 4H2OG plus 4H2L, every atom accounted for.
Perfect. And beyond balancing, chemists also look for patterns, common types of reactions.
Right, recognizing patterns makes things easier, like the main types.
Yeah, 3 really common ones are combination, decomposition, and combustion.
Combination sounds straightforward.
It is. 2 or more things combine to make one more complex thing, like our NH3 plus HCl example earlier, forming NH4Cl, or nitrogen and hydrogen making ammonia, N2 plus 3H2 NH3.
And decomposition.
The exact opposite. One complex thing breaks down into 2 or more simpler things, like heating calcium carbonate, limestone. KCO3 breaks down into CaO and CO2.
Okay, and combustion, that's burning, right?
Usually, yes. Burning in oxygen, If your starting material has carbon and hydrogen or carbon, hydrogen, and oxygen, you typically get carbon dioxide and water.
Like burning methane, natural gas. CH4 plus 2O2, ACO2 plus 2H2O.
Classic example. Recognizing these types helps you predict products pretty quickly.
So balancing lets us track atoms. Reaction types help predict outcomes. But how do we know the formula of a compound in the first place, especially if it's something new?
That often involves a technique called combustion analysis, especially useful for organic compounds, things with carbon and hydrogen, maybe oxygen.
How does that work? Sounds complex.
The setup is clever. You take a very precisely weighed sample of your unknown stuff, burn it completely in pure oxygen.
Okay.
All the carbon in your sample becomes CO2, while the hydrogen becomes H2O. And you have special traps that absorb the CO2 and H2O produced, and you weigh them.
Ah, I see. So the mass of CO2 tells you the mass of carbon you started with.
Exactly. And the mass of H2O tells you the mass of hydrogen. Because where else could they have come from? They had to be in your original sample.
Right. But what about oxygen? If the compound had oxygen?
That's the tricky bit. The oxygen in the CO2 and H2O could have come from your sample or from the O2 you used for burning, so you can't measure it directly from the product.
So how do you find it?
By subtraction. You know the total starting mass of your sample. You just calculated the mass of carbon and the mass of hydrogen in it. If you subtract those from the total, anything left over must be the mass of oxygen that was originally in the sample.
Clever. So now you have the mass of C, H, and maybe O.
Then you convert those masses to moles. And the mole ratio gives you the simplest whole number ratio of atoms, the empirical formula.
Like for glucose, they found it was CH2O.
Right, that's the empirical formula. But if you also know the compound's molar mass, maybe from another experiment, you can figure out the actual molecular formula.
Oh.
Well, the empirical formula CH2O has a mass of about 30 gmol. Glucose has a molar mass around 180 gmol.
1 divided by 30 is 6.
Exactly. So you multiply the subscripts in the empirical formula by 6. CH2O becomes C6H12O6. That's glucose.
That's really powerful, like chemical detective work.
It is. It lets us figure out what new substances are made of.
Okay, so we know how to identify and write formulas and balance equations. Now, back to that fugu toxin question, predicting how much. That's stoichiometry, right?
Yeah, stoichiometry is all about the quantitative relationships and reactions. The balanced equation is the key. It gives you the mole ratios.
So coefficients.
Exactly. Those coefficients tell you the proportions. If the equation says 2A plus B A3C, it means 2 moles of A react with 1 mole of B to make 3 moles of C. That ratio is fixed.
So you can use it like a conversion factor?
Precisely. If you know how many moles of A you have, you can calculate exactly how many moles of C you should make or how many moles of B you'll need.
And in the lab, we measure in grams, usually.
Right. So the typical path is grams of reactant, moles of reactant using molar mass, moles of product using the mole ratio from the balanced equation, A grams of product using molar mass again.
It's a roadmap for calculation, like making laughing gas, N2O from ammonium nitrate, NH4NO3.
Right. The balanced equation is NH4NO3s plus 2H2OG.
Yeah.
If you wanted to make, say, 10.0 grams of N2O.
You'd convert 10.0 gram N2O to moles, use the 1.1 mole ratio to find moles of NH4NO3 needed, then convert that back to grams.
Exactly. And you could also figure out how much water you'd produce at the same time. It's incredibly practical.
But, in the real world, you don't always mix things in those perfect ratios from the equation.
Almost never. Which brings us to limiting reactants.
Okay, what does that mean?
It means one of your reactants is going to run out before the others. It limits how much product you can possibly make.
Like making sandwiches. If you have 10 slices of bread but only 3 slices of cheese, you can only make 3 cheese sandwiches. The cheese is limiting.
Perfect analogy. The reactant that gets completely used up is the limiting reactant. The ones you have extra of are the excess reactants.
So how do you figure out which one is limiting in a chemical reaction?
You take the starting amount of each reactant and calculate how much product you could make if it reacted completely. Whichever reactant produces the smallest amount of product is your limiting reactant.
Makes sense. That's the bottleneck.
Let's take Alka-Seltzer. It's sodium bicarbonate, NiHCO3, reacting with citric acid, H3C6H5O7, to make CO2 gas.
The fizzing.
Right. Say you have 1.770 grams of NiHCO3 and 1.0 gram of citric acid. The balanced equation is 3NHCO3 plus H3C6H5O7 plus 3H2O plus 9A36H5O7.
Okay, lots of 3s there.
So you calculate moles of CO2 from 1.7700 gram NiHCO3. Then you calculate moles of CO2 from 1.00 grams citric acid. Whichever calculation gives fewer moles of CO2.
That reactant ran out first. That's the limiting one.
Turns out, in this case, it's the citric acid. It limits the CO2 production.
Which means you'll have some sodium bicarbonate left over when the fizzing stops.
Exactly. You can even calculate how much is left over. And crucially, all calculations for how much product you can make must be based on the starting amount of the limiting reactant.
Super important for industry, I bet. You want to base your expected output on what actually limits production.
Absolutely. You don't want to run out of your most expensive reactant first, usually.
Okay, so the limiting reactant determines the maximum possible product. What's that called?
That maximum amount, calculated from stoichiometry, assuming everything goes perfectly, is the theoretical yield.
Theoretical, meaning it doesn't always happen.
Rarely perfectly. In reality, the amount you actually get when you do the reaction in the lab or factory is the actual yield.
And the actual is usually less than the theoretical.
Almost always. Why? Well, maybe the reaction doesn't go to completion. Maybe some side reactions happen, making stuff you don't want. Or maybe you just can't collect and purify all the product. Some gets lost during handling.
Right, spilling a bit, stuff sticking to glassware.
All those practical things add up. It puts those tiny yields for the fugu toxin synthesis into perspective, doesn't it? Lots of steps, lots of places for losses.
So how do chemists talk about how well a reaction actually worked?
They use percent yield. It's a measure of efficiency.
How do you calculate it?
Simple ratio. Percent yield, actual yield, theoretical yield, X, 100%.
Okay. So if you theoretically could make 100 grams of aspirin, but you only actually collected 80 grams.
Your percent yield is 80%. It tells you how close you got to the maximum possible.
So knowing the theoretical yield is important even if you don't reach it because it gives you a benchmark.
Exactly. It tells you how efficient your process was.
Now, you mentioned efficiency. Is there another way to think about it? Something about atoms.
Ah, yes. Atom economy. This is a concept from green chemistry, which is all about designing chemical processes to be less wasteful and hazardous.
How is it different from percent yield?
Percent yield focuses on the limiting reactant, how much of it turned into the product you want. Atom economy looks at all the reactants. It asks, what percentage of the total mass of all your starting materials actually ends up in the desired product?
So it's about minimizing waste from all starting materials.
Exactly. Imagine a reaction A plus B, E plus D. If C is your desired product, but D is just waste, even if you get 100% yield based on limiting reactant A, your atom economy might be low if reactant B or byproduct D has a high mass.
Give me an example.
An older way to make phenol, an important industrial chemical, had an atom economy around 37%. A lot of the mass of the starting materials ended up as unwanted byproducts. But a newer process makes phenol and acetone, which is also a valuable chemical. Because both products are useful, its atom economy is essentially 100%. All the starting atoms end up in useful stuff.
Wow, that's a big difference.
Huge. Same idea with ibuprofen synthesis. The old way was around 40% atom economy. The newer, greener process is over 77%, even higher if you recycle a byproduct. It's about designing smarter reactions that use materials efficiently.
A very modern challenge in chemistry. Less waste, better use of resources.
Definitely.
Okay, shifting gears a bit. We've talked calculations, efficiency. What about predicting reactivity itself? Can the periodic table help?
Absolutely. The periodic table isn't just a list. It's packed with predictive power based on underlying atomic properties like ionization energy and electron affinity.
Ionization energy, how hard it is to remove an electron.
Right. And electron affinity, how much an atom wants to gain an electron.
So sodium has low ionization energy, easily loses an electron. Chlorine has high electron affinity, readily gains one.
And boom, they react readily to form ionic sodium chloride, NaCl. Those properties predict their behavior.
And there are trends across the table.
Big time. The most general rule, elements in the same group column tend to react similarly because they have the same number of valence electrons, the outer ones involved in bonding.
But are there exceptions?
Oh, yes. Chemistry loves exceptions. A key one is that the first element in each main group often behaves a bit differently from the rest. It's usually much smaller.
Like lithium in group 1.
Exactly. Unlike the other alkali metals below it, lithium reacts directly with nitrogen gas. That's unique behavior linked to its small size.
Interesting. Any other weird patterns?
There are also diagonal relationships. Elements in period 2 show some similarities to elements diagonally below them in period 3. Lithium is like magnesium, beryllium like aluminum, boron like silicon.
Why's that?
It's often due to similar charge densities, the ratio of charge to size. It shows the table's patterns are complex and interconnected.
So let's look at some groups. Group 1A, alkali metals.
Super reactive. Low ionization energies, never found pure in nature. react vigorously, sometimes explosively with water. Reactivity increases down the group.
And group 1b, copper, silver, gold. They also have one valence electron.
Ah, but they are much less reactive. Think about it, gold doesn't corrode easily.
Why the difference if the outer electron count is the same?
It's about shielding. The inner-outer electrons in group 1b aren't as good at shielding the outer electron from the nucleus's pull compared to the noble gas cores in group 1a.
So the outer electron in copper or gold is held more tightly.
Much more tightly, higher ionization energy, less likely to react. That's why they're coinage metals, often found uncombined. It's a beautiful example of how inner electron structure affects outward reactivity.
Fascinating. What about the other side, group 7a, halogens?
Very reactive nonmetals. Fluorine, chlorine, bromine, iodine. By electron affinities, they really want to gain an electron to complete their outer shell. Form X ions easily. React with metals to form salts. React with hydrogen to form hydrogen halides like HCl.
And group 8a, noble gases, the inert ones.
Well, inert was the old thinking. They have full valence shells, very stable. But since the 1960s, we know xenon and krypton can be forced to react, but only with extremely reactive elements like fluorine or oxygen. It takes a lot.
So the table predicts general trends, but there are always these interesting nuances and exceptions.
That's what makes chemistry interesting. The patterns provide a framework, but the details matter.
So it really seems like understanding these core concepts, equations, stoichiometry, yields, periodic trends, gives you a powerful lens for viewing the chemical world.
Absolutely. We started with that fugu toxin, seemingly complex and low yield.
And we saw how balancing equations is fundamental, based on conserving atoms.
Then how combustion analysis lets us figure out formulas, real chemical detective work.
And stoichiometry allows us to calculate how much, leading into the practicalities of limiting reactants and actual versus theoretical yield.
Plus the modern push for efficiency with atom economy.
Finally, connecting it all back to the periodic table, understanding how electron configurations and properties like ionization energy predict how elements will behave, with those interesting comparisons like group 1a versus 1b.
You really do gain a toolkit for interpreting chemical language and predicting outcomes.
You now have that foundation, how chemists think, analyze, predict. It's about understanding the why and how much behind chemical change.
So now that you've glimpsed this intricate dance of reactions, think about what's happening around you right now.
Like breathing, or your body metabolizing lunch, or just rust forming on metal.
Exactly. What unseen chemical reactions are shaping your world constantly? And how could understanding them better lead to, well, new ideas or solutions?
Something to mull over. Until next time, keep diving deep.